We've been talking about the simple gas laws. There's the train. And we can look at those. Volume is proportional to 1 over pressure. Volume is directly proportional to temperature. The volume is proportional to the amount of gas in moles. If we combine all of those together, we can say that the volume is proportional to NT over P. To turn a proportionality into an equality, you need to add a constant. And so this constant would be R. So V equals a constant times NT over P. So that's the ideal gas law, but we usually rearrange it and look at it this way. PV equals nRT. And that's what's referred to as the ideal gas constant, and that is, the ideal gas law, and that is an important equation. So R can have different values, just like if you measure the length of a piece of paper. It could be 12 inches, or it could be 1 foot. The number changes when the units change. So the value of R depends on the units that are used. We're going to use R equals 0.08206. Units are liter atmospheres times mole Kelvin. And those units seem kind of messy, but when we use liters for volume, atmospheres for pressure, moles for amount of gas, and Kelvin for temperature, then all the units cancel out correctly. Any questions? Yeah.
So, isn't there some situations to where you can remove, like if they say that, like pressure and temperature are constant,
Mm-hmm.
like not even use them?
Yes, if pressure and temperature are constant, then you're going to have one of the simple gas laws. And I will show you later how you can quite easily derive all of the simple gas laws from the ideal gas law. So you actually don't need to remember any of the rest of them if you remember PV equals nRT. We're showing how from the ideal gas, so if you have constant pressure and temperature, you end up with Avogadro's law. Constant N and P, you end up with Charles' law. Constant N and T, you end up with Boyle's law. So how does that work? Well, let's think about it this way. We know that PV equals nRT. And I'm just going to change color, and it's still the same, it's still equal if I write it in red ink, right? If I take one equality and divide it by another equality, then these two things are still equal, right? Because PV is equal to nRT, then I'm dividing both sides by the same thing, it's still equal. Okay with that? Now, is R going to change? No, because it's a constant, right? So we can get R out of there. R is going to cancel out. So we've got the black values and the red values. If, let's do this one. If the pressure and the temperature are constant, so the pressure and the temperature are constant. So if the pressure before and after, we could think of these as 2s and 1s. One. So if pressure 1 is equal to pressure 2, then those cancel out, right? So that's gone. And if temperature 2 is equal to temperature 1, then that would be gone, right? Because whatever it is, it would cancel out. And what am I left with? I'm left with a different rearrangement of Avogadro's law. If I swap sides here, I'm going to get V1 over N1 equals V2 over N2, and that's how we learned Avogadro's law. So to derive any equation that you need, you just take the ideal gas law, P1 V1 equals N2 R T2. Oops. Oh my goodness, it's going to be a long day. You got to get ones all across the top and twos all across the bottom. I'm not putting a number on R because it doesn't change, it's a constant. So I took the ideal gas law and I divided it by itself, and now I'm just going to cross off anything that doesn't change. Right? So R doesn't change, so cancel out R. Let's look at this scenario where N and T. You got a question?
Does R always cancel? Or?
R always cancels because R is a constant, it's always the same. Yeah. And that's why we didn't see R in any of the simple gas laws, because those are looking at just relationships between changing quantities, and so the R's cancel out. So if we look at this and we have constant N and constant T, well, that means that the amount of gas before and after the change is the same. So the N1 equals N2, so that cancels out. And the temperature before and after is also the same. So T1 cancels out T2. What's left on the right side of that equal sign? 1. So now all of that is equal to 1. So if I cross multiply, P1 V1 is equal to P2 V2. And that's Boyle's law. See how that works? Everybody's a little dazed. Okay. Let's do an example. An 8.50 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What's the pressure in atmospheres and psi of the gas in the tire? Well, in previous examples, we made a table to organize the information here. So we can take that approach again. Sketch out a table here with row 1 and row 2, and then just collect the numbers. So 8.50 liters. What is that quantity? Pressure, volume, temperature, or amount? That's the volume. So I'll label that column V. And then I got 0.552 moles of gas, and we call that N, right? And then they're saying the temperature is 305 Kelvin. So that's the temperature. I have run out of numbers. There's nothing to put in the bottom row because nothing's changing. This is an ideal gas law problem. If you don't recognize what kind of a law problem it is, you can still start making a table, and that'll clue you into what sort of an equation you need. Here, I'm not going to have any 1s and 2s. It's not really a waste of time, though. I'm just going to go ahead and erase the rest of that table because I don't need it. Because what I have done is I have organized and labeled my data. So this is the volume, this is N, and that's T. The question's saying, what is the pressure? So I need an equation that has all the variables in it, and that's the ideal gas law. So PV equals nRT. I have volume, I have N, I have T, I know what R is, so I can solve for V. So I'll rearrange this equation. I'll divide both sides by volume because I'm solving for P. So the volumes cancel out. So the pressure is equal to nRT over V. So I'm going to put my numbers in here, including their units. So N is 0.552 moles. R, it's a good idea to memorize that. 0.08206. The units are kind of messy, but write them in anyway. Liter atmospheres per mole Kelvin. And the temperature, 305 Kelvin. And then all of that divided by the volume, 8.50 liters. Yeah.
I guess where I got confused is that 0.08206, that's R, correct?
That's R. Mm-hmm.
So I thought that we didn't use it then because it was constant. So we still use it, it's just constant.
Well, we use it, yeah, it just it doesn't change. So if we don't have R, we know that the pressure is proportional to N, T, and V, but we can't say what the pressure is. So before we do any math, we should check the units.
Yeah, how did you come up with R?
R is because I'm telling you this is what it is.
R just is, it's a constant.
So is R always going to be that?
Yeah.
That's what constant means. It's constant, it doesn't change. So this is just what it is, because we if you measure the pressure, the amount of gas, the temperature, and the volume, and you use this equation, it doesn't matter what scenario you're using, R is always the same. The only time R can change the number, we'll see later in a later chapter, we're going to see that we'll have an R of 8.314, but there we're going to have joules per mole Kelvin as the unit. So it's only going to change its number because the units are going to be different. So that's like measuring a piece of wood and saying, well, this is 2 feet long, and somebody else says, no, it isn't, it's 24 inches long. Are those different? No, they're the same, right? So the units can make the number different, but this is a constant. So that's our constant, R. And R tells us what units we have to use for the other things. So always write in your units, and then let's make sure that they're going to cancel out correctly. So here's moles and moles. Those are going to cancel. And the kelvins are going to cancel. And the liters are going to cancel. And I'm left with atmospheres, which is a unit of pressure, and so that's a really good sign. So 0.552 times 0.08206 times 305 divided by 8.5. R is not an exact number. As it's written here, it's got 4 significant figures. All my other numbers had 3 significant figures. So my answer is going to have 3. I'll write down 1.62, 2 digits just because, and round that to 1.63 atmospheres. Any questions? I forgot the last part of this example yesterday. It asks for the pressure in atmospheres and PSI. So when I calculate PSI, I want to use the unrounded pressure. So 1.6253 atmospheres. To convert to PSI is always one step. So I want PSI on top and atmospheres on the bottom. 1 atmosphere is 14.7 PSI. I don't expect you to remember that. We got 1.6253 times 14.7.
So we won't have something like that in the test?
No, you could have something like this on the test, but I'll give you the conversion factor. So again, 3 sig figs there, and so I'd round that to 24.0 PSI. Any questions? Yeah.
How about the last one and the
The conversion factors for millimeters of mercury? Yeah, I've already told you, you need to know this, that 1 atmosphere equals 760 torr, which equals 760 millimeters of mercury. You need to memorize that one. This is the only one you have to memorize. If you need any other pressure unit conversions, I'll give those to you. Yeah.
When we're running to 3 sig figs, is it 23.9 or the 20, or do we run it off to the 22?
Yeah, I screwed up. Thank you for pointing that out because that's not right. I got a little carried away. The 9 rounds the 8 up to a 9 is 23.9. Thank you. Any other questions? Let's do another one. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters mercury and a temperature of 58 degrees Celsius? Well, let's collect numbers and identify them. So we've got 0.556 moles of a gas. Well, the amount of gas in moles is called N. The pressure equals 715 millimeters of mercury. The temperature equals 58 degrees Celsius. So we know that R equals 0.08206 liter atmospheres per mole Kelvin. Those are the units we need for our other quantities. So N is in moles, that's good. Can we use millimeters of mercury for the pressure? No, because that unit won't cancel with atmospheres, so it's not going to work. We need to convert to atmospheres. So multiply by atmospheres, divide by millimeters of mercury. 1 atmosphere, 760 millimeters of mercury. That is an exact relationship. So it won't limit our sig figs. So 760, good grief, 760. 715 divided by 760. 0.94078 atmospheres. I want to keep some extra digits because I'm going to use this in an equation. This reminds us that we have to put our temperature in kelvins, so I need to convert this to Kelvin. Since this is to the nearest 1 degree, I'm going to be lazy and just use 273 instead of 273.15. You can always use 273.15. It's not going to hurt anything. So 331 Kelvin. I need the ideal gas law, PV equals nRT. And I am looking for the volume this time. So I'm going to divide both sides by P to get V by itself. It's always best to rearrange when you're just dealing with letters instead of when you've got numbers and units. Volume equals nRT over P. So that's 0.556 moles. Ooh, I hope I can fit this in. 0.08206. That's not going to work. I have to write it down here. 0.556 moles. 0.08206 liter atmospheres per mole Kelvin. And 331 Kelvin. divided by the pressure in atmospheres. Check the units. Atmospheres cancel, moles cancel, kelvins cancel. And I'll get my calculator to do the math for me. 0.556 times 0.08206 times 331 divided by 0.94078 equals. All the numbers I was given, well, let me take that back. The amount of gas and the pressure had 3 significant figures. The temperature had 2 significant figures. But when I convert to Kelvin, this is adding, and so this temperature has 3 significant figures. That happens a lot. This has 4. So my answer should have 3 sig figs, 16.052 liters, rounding to 16.1 liters. And that's the volume. Any questions?